If you peel back the layers of the world around you, from the medicine in your cabinet to the materials in a quarry, you will eventually find a microscopic piece of pure geometry. It's a chemical chassis known as aromatic benzene. In its bare, isolated form, you might not give it a second glance. It sits in a beaker as a totally transparent liquid. It has a surprisingly sweet, pleasant smell, and if you light it, it burns with a thick, heavy black smoke. This animated blueprint shows us exactly why that smoke is so black. The molecule is packed with carbon. It uses 6 carbon atoms to form a rigid hexagon, with 6 hydrogen atoms pointing outward. To hold this shape together, the carbons rely on an alternating pattern of double bonds. But those double bonds don't sit still. Through a feature called resonance, the atoms constantly share their electrons back and forth. Think of the spokes on a bicycle wheel spinning so fast they blur into a single solid shield. Benzene's value comes from this stubborn stability. It provides a consistent foundation that chemists can rely on to stay intact while they build complex structures around it. Before anyone can start building with this platform, they have to go out and get it. Chemists have to extract this exact 6-sided shape from raw, carbon-rich materials. This photograph shows one of the oldest methods of finding it. Heating coal without air produces a heavy, black sludge called coal tar. Through a process called fractional distillation, they boil that sludge until the pure benzene evaporates out. And right here in this refinery, we see the other massive industrial approach. Here, they take standard petroleum liquids, like normal hexane, and push them over a platinum catalyst at high heat, forcing those loose carbon chains to snap together into our perfect hexagon. Of course, a chemist doesn't always need a refinery. Right at their lab bench, they can take a molecule called phenol, sprinkle in some hot zinc dust to strip away the oxygen, and isolate the same 6-sided chassis in a beaker. Whether it takes tons of coal or a few pinches of zinc, the result is the same. We get a stable, glowing molecular chassis, ready to be programmed. Once you have the benzene board, you discover its primary rule. The system resists any attempt to force new atoms inside its ring. Look closely at this animation. Chemists can force new elements into the molecule through an addition reaction, but it requires extreme heat or intense UV light. Under that stress, the central spinning shield finally shatters, so new atoms can jam inside. When that inner shield breaks, the molecule loses its special stability. It effectively downgrades into ordinary, highly reactive chemicals like cyclohexane or a common insecticide. By destroying the chassis, you lose the very properties that make benzene useful. To actually build with it, chemists needed a way to attach new components without breaking the foundation. The solution was to ignore the protected inner ring entirely. Instead, chemists learned to utilize the 6 hydrogen atoms sitting on the outside.
This diagram shows a much more elegant approach, called a substitution reaction. Think of the outside of the hexagon as a series of ports. One single hydrogen atom pops right off, leaving an open space, while the core remains untouched. Into that open space, you can plug whatever you want. Slide in a chlorine atom, and you have chlorobenzene. Swap that for an alkyl group, essentially a small, oily carbon chain, and you have toluene. Substitution allows for modular customization. It lets chemists swap parts in and out without compromising the core structural integrity of the hexagon. But there is a catch. When you have 5 open ports, where do the new pieces go? The rule is surprisingly strict. The very first module you plug into the board takes control over the rest. Notice in this animated diagram how that first piece acts as a system admin. It dictates exactly which of the remaining ports will accept new connections, the 2 right next door, the 2 that are 1 space away, or the single port sitting directly across the board. The commands are highly specific. Oily carbon chains, like alkyls, route new connections to the spots next door, called ortho, or the spot directly across, called para. Other pieces, like nitros, which are nitrogen-based clusters often found in explosives, strictly open the metaports 1 space away. This means chemical reactions are not random. Building complex molecules is a game of following the exact routing rules set by that first system admin. When you understand these strict routing rules, you can design powerful structures. Let's see how this logic builds a famously destructive molecule. Watch this. We plug a methyl group into the top port of our benzene chassis. This admin wakes up the two adjacent ports and the one across the bottom. Next, it routes 3 nitro groups into those exact open slots. The result? Trinitrotoluene, TNT. This photograph of artillery shells shows why this molecular arrangement is volatile. Chemists tightly packed carbon fuel and oxygen into one single, cramped package. The bonds holding those nitrogen groups to the outside are relatively weak. The moment a spark hits them, they snap off and form hyper-strong gases. That shift releases heat and pressure so fast it creates an explosion. The beauty of a blank board is it doesn't care what software you run. By clearing the board, we can use these same rules to build something you use every day. This diagram shows the assembly of a common detergent. Chemists plug in an alkyl group, which acts as a tail that attracts grease and oil. Across from it, they attach a sulfonic acid group, a special connector that grips onto water. This stable hexagon is the bridge inside everyday laundry soap. It traps oil on one side, washing away as the other clings to water. By working with benzene's stable core and the specific rules for swapping its outer ports, chemists gained a precise method for assembling the materials that define the modern world.